Hello. Public key certificates are the most commonly used method for distributing public keys. Even though the concept of a public key certificate is quite straightforward, managing and distributing them in large-scale applications can present several challenges. In today's video, we'll explore public key infrastructures, or PKI, a framework that combines cryptographic protocols, policies, technology, and supporting services to ensure the safe and reliable use of certificates. By key management, I mean the techniques and procedures involved in the creation, distribution, storage, and updating of cryptographic keys. This video focuses on managing public keys. These keys might be used for public key encryption, key agreement, or signatures. The most common application is using public keys to verify digital signatures. In the previous video, we saw two examples highlighting the importance of authenticating public keys that are used to verify digital signatures. The first example was of establishing a secure communications channel. Alice and Bob exchange authenticated public keys, which serve as verification keys for a signature scheme such as ECDSA. They then perform the authenticated elliptic curve Diffie-Hellman protocol, ECDH. So Alice sends Bob a randomly selected elliptic curve point X, along with her signature on X. Bob checks Alice's signature using Alice's public verification key. Similarly, Bob sends Alice a randomly selected elliptic curve point Y, along with his signature on Y. Using their respective secret keys x and y, they compute a shared secret key k. Thereafter, for the remainder of the communications session, they encrypt and authenticate data for each other using AES-GCM. You should appreciate the critical importance of Alice and Bob possessing authentic copies of each other's public verification keys. The second example demonstrating the importance of authenticating public keys is software updates. A software company such as Microsoft can conveniently distribute software updates to hundreds of millions of computers worldwide by broadcasting a digitally signed copy of the software. Any recipient who possesses an authentic copy of Microsoft's public verification key can verify the digital signature, ensuring that the software update is genuinely from Microsoft and isn't malware. Once again, you should appreciate the critical importance of recipients possessing an authentic copy of Microsoft's public verification key. I'll briefly mention three additional examples where public keys are used to verify digital signatures. The first example is FIDO, an alliance of companies working to reduce the reliance on passwords for user authentication in web applications. In FIDO, the user Alice generates a public-private key pair for the ECDSA signature scheme and securely registers her public key with the website. At a later time, when Alice logs into the website, she authenticates herself by signing a random challenge issued by the website. The website verifies the response using the stored copy of Alice's public key. In addition, since a random challenge is issued for each login attempt, replay attacks are prevented. The second example is ePassports as designed by the International Civil Aviation Organization, ICAO. Alice's biographical information is digitally signed by an accredited document signer from the country that issued her passport. The signed data is embedded in a chip within her ePassport. When Alice arrives at a border checkpoint, the immigration authorities verify the signed document using the document signer's public key. For this verification to be reliable, the immigration authority must possess an authentic copy of the signer's public key. The third example is code signing. Apple carefully verifies the real-world identity of app developers and requires the app developers to sign their code. When a developer submits a piece of code to the Apple Store, Apple can validate that the code is authentic using the developer's public verification key that Apple has certified. If the signature is valid, then Apple adds the app to their web store. This serves as a deterrent to the creation of malicious apps. There are several methods for distributing public keys in large-scale applications. The public key can be delivered by a trusted courier or provided to a user during a one-time registration. It might also be pre-installed in a browser or operating system. In some cases, two parties can verify each other's public keys through visual inspection. For example, in the WhatsApp messaging app, users compare hashes of each other's public keys. We'll explore this further in the video on Signal. Another approach is including the public key in a file that is digitally signed by a trusted entity. This file can be made available on a public website, allowing anyone to download and verify its authenticity using the trusted entity's public signature verification key. There might be a service in place whereby a user can send real-time requests to verify the authenticity and validity of a public key. An online trusted server would verify the public key and send a digitally signed confirmation to the user. The remainder of this video will focus on offline certification authorities, or CAs. These are trusted entities that issue certificates that attest to the authenticity of public keys. A public key certificate is a digital document issued by a certification authority. The document cryptographically binds together an entity's identity to its public key, along with some relevant attributes, in a manner that allows other entities to gain trust in the public key's authenticity. A PKI is a comprehensive framework that combines cryptographic protocols, technology, policies, and supporting services, such as legal and business processes, to ensure the secure and reliable use of public key certificates.
A public key infrastructure consists of several components. The most important ones are certificate format, certification authority, certification process, mechanism for certificate revocation, trust model, certificate policy, and certification practice statement. We'll explore the first 5 components in this video. An example of a certification practice statement will be given in the next video.
A standardized certificate format is essential for ensuring the certificate data is machine readable and can be processed and used across different applications. This promotes interoperability. In practice, X509 certificate formats are widely adopted. An X509 certificate contains the following components: a version number, a serial number that uniquely identifies the certificate among ones issued by that CA, the distinguished name of the CA that issued the certificate, the validity period of the certificate, including a start date and an expiration date, the distinguished name of the entity to which the certificate is issued, the algorithm to be used with the subject's public key, the subject's public key, and the signature algorithm used by the CA. X509 defines many other attributes that might be useful in limiting the use and scope of the public key that is certified. For example, an attribute might specify that the certificate subject can only sign financial transactions that have a value of at most $1,000. Finally, the certificate includes the CA's digital signature on the other data fields in the certificate. The concept of a certificate is quite straightforward. A certification authority, or CA, is a trusted entity that issues certificates that bind together Alice's identity to her public key. Alice's certificate consists of 2 parts. The data part which contains her identifier, her public key, and other information like the certificate validity period. And the signature part is the CA signature on the data part. After the certificate has been created, a user Bob can obtain an authentic copy of Alice's public key as follows. We assume that Bob has somehow been able to obtain an authentic copy of the CA's public verification key. Bob then obtains Alice's certificate, perhaps from an untrusted source. He verifies the authenticity of the CA signature using the CA's public verification key. If the signature verifies, then Bob is confident that he has an authentic copy of Alice's public key.
In this context, the CA's public key is sometimes called a trust anchor. Anyone who possesses an authentic copy of the CA's public key can leverage it to verify the authenticity of public keys in all the certificates issued by that CA. In practice, trust anchor CA public keys are typically distributed by non-cryptographic means, for example by embedding them in a browser or an operating system.
It's important to note that the CA does not have to be trusted with users' private keys. However, CAs must be trusted not to issue fraudulent certificates, either intentionally or due to incompetence. An ideal certificate issuance process involves several critical steps to ensure the proper use of certificates. At the beginning, the CA generates its public-private key pair for a signature scheme such as RSA or ECDSA. Protecting the CA's private signing key is of utmost importance, as it is used to sign all issued certificates. To enhance security, this private key is often generated and stored within a hardware security module, or HSM. This is a tamper-resistant device that securely stores cryptographic keys and performs cryptographic operations with the keys. To mitigate the possible loss or destruction of the CA's private key, copies of the key should be stored in HSMs located in different geographical locations.
Alternatively, a threshold signature scheme could be used. In such a scheme, shares of the private key are generated and stored in different locations. To sign a certificate, a subset of shares are used to generate shares of the signature. The signature can then be assembled using the signature shares. Notably, the signing key itself is never generated or stored in one location.
The CA is now ready to issue certificates. An entity Alice requests a certificate for her public key. This request should be authenticated. Ideally, the CA should also maintain a record of the request, which can be used to resolve disputes, such as when a user denies having requested a certificate. Next, the CA carefully verifies Alice's identity, which may involve examining paper documents such as her driver's license or passport, or other digital credentials. In large-scale applications, the identity verification process might be delegated to a registration authority or an intermediate CA. The CA or the RA verifies that Alice's public key is valid, meaning that it has the necessary mathematical properties for a corresponding private key to exist. Alice then demonstrates possession of her private key, perhaps by signing a message that the CA can verify using Alice's public key. Finally, the CA issues Alice a certificate by signing a message that includes Alice's identifier, her public key, and other pertinent information, such as the certificate's expiration date. An entity relies on the certificate to obtain an authentic copy of the certificate subject's public key. Let's suppose that the public key is a verification key for a signature scheme. Because the certificate has an expiration date, the relying party can trust that the public key remains valid, meaning that the certificate subject is authorized to sign messages as long as the expiration date hasn't passed. However, a CA may wish to invalidate a certificate before its scheduled expiration date. This is called certificate revocation. In practice, there are several reasons to revoke a certificate. For instance, the certificate subject's private key might have been compromised. In 2014, the Heartbleed bug was exploited, and it is estimated that more than 500,000 TLS private keys were compromised. The certificates for the corresponding server public keys had to be revoked. A certificate might also be revoked when the subject leaves an organization or changes roles within it. So a relying party needs the assurance that a certificate that they are verifying has not been revoked prior to its expiration. There are 3 common methods to inform relying parties about revoked certificates. First, certificates could be issued with a very short validity period, so there wouldn't be a need to revoke a compromised certificate since it will expire soon anyways. Second, an online server can be queried to confirm that a certificate has not been revoked. The Online Certificate Status Protocol, OCSP, is a standardized protocol for checking certificate status online. Third, certificate revocation lists, CRLs, can be used. This is the most widely adopted method for certificate revocation. The concept of a CRL is fairly simple. A certificate revocation list is a list of certificates that have been revoked before their scheduled expiration dates. The CRL is issued and signed by a CA and updated at regular intervals. Before relying on a certificate, an entity should check that the certificate is not listed in the latest CRL. Even though they are conceptually simple, CRLs can be challenging to manage in large-scale PKI deployments. One challenge is the time granularity, meaning the delay between when a certificate is revoked and when the CRL is updated. Another challenge is that the CRL can grow excessively large over time. There are many methods to address these issues, but I won't be discussing them any further. The last topic of this lecture is CA trust models. The simplest trust model is a single CA who issues certificates to end users, A1, A2, and so on. A real-world example is Apple's code signing process. In this model, Apple serves as a CA and issues certificates for the public verification keys of app developers. When a developer submits their code to the Apple Store, they sign their code. The Apple Store can verify the signature to ensure that the code comes from an authorized developer. In the single root hierarchical CA model, a root CA issues certificates to intermediate CAs. The intermediate CAs in turn issue certificates to end users. Intermediate CAs are used for several reasons, including distributing workload, reducing risk, and separating functions within the PKI. To obtain an authentic copy of an end user's public key, for example, A2's public key, one needs A2 certificate, the certificate of its issuing intermediate CA ICA1, and an authentic copy of the root CA's public key. One then uses the root CA's public key to verify ICA1 certificate, thus verifying the authenticity of ICA1's public key. Finally, one uses ICA1's public key to verify A2 certificate, thus verifying the authenticity of A2's public key. This is an example of a two-level certificate chain, but additional levels can be introduced for more complex trust hierarchies. In the multi-root hierarchical CA model, multiple single-root CA hierarchies operate independently each managing certificates for end users within its domain. To establish trust across these separate hierarchies, root CAs can cross-certify each other. This means that if one possesses an authentic copy of, let's say, root CA1's public key, then one can use the appropriate chain of certificates to verify the authenticity of public keys belonging to end users in CA2's domain. A real-world example of the multi-root hierarchical CA model is the ePassport PKI designed by the International Civil Aviation Organization. In this system, each participating country operates its own two-level single-root CA hierarchy. The country signing certificate authority, CSCA, serves as the root CA and issues certificates to document signers within that country. Document signers are responsible for signing the biographical data stored in passports of citizens of that country. To enhance security, it is recommended that a document signer operate for no more than 3 months or sign at most 100,000 travel documents, whichever comes first. The signed biographical data, along with the document signer certificate, is embedded in the ePassport. To verify an ePassport's authenticity, border control agencies require the CSCA's public key. The CSCA public keys of all participating countries are distributed via a public key directory, which is also used to share certificate revocation lists. Another real-world example of a multi-root hierarchical CA model is WebPKI, which I'll cover in the next video.
I hope that this video has given you a good appreciation of the many challenges involved in deploying a PKI at scale. Many of these challenges stem from business, legal, and usability considerations, including interoperability, which can be improved through standardized and flexible certificate formats, managing certificate revocation lists to handle compromised certificates, using hardware security modules to securely generate and use CA private signing keys, business and liability concerns associated with cross-certification between CAs, and the transition to quantum-safe cryptographic algorithms, a process that is already underway.